This is Algebra 2 with trig. This is the review for the absolute value functions. Unit 1. So there's different ways we can graph an absolute value. I'm going to use an RST format. So I'm going to start with the parent function. So that's y equals absolute value of x. I ask that you graph the absolute value function, the parent function, and now we're going to do a reflection. So that means we come over the x-axis, multiply all the y values by a negative, and that's going to bring your parent function reflected over the x-axis. So now we're going to have y equals negative absolute value of x. Then we're going to take every one of those points and translate it. 1 to the left and 3 down. 1 to the left and 3 down. And we continue that pattern of 1 to the left and 3 down for every single point that we have. And we have negative absolute value of x plus 1 minus 3. Our domain of this red graph, absolute value functions are always all real numbers. The range is from this highest point, which happens to be negative 3, and down. So your y value is less than or equal to negative 3. In terms of interval notation, you could use negative 3 with the square bracket. Actually, sorry, you put the smallest number first, which is negative infinity, with a rounded bracket. And then that comes up to the maximum value of negative 3, and it can equal that one. For all real numbers, you go from negative infinity to positive infinity, because it's all real numbers. It's every number. So here we'll start out again with the parent function. If you need to make a table to form the parent function, that's fine. Otherwise, I'm not a big fan of making a table and just plotting your points. For Algebra 2, we can handle that by understanding how these translations and other transformations work. So we take our parent function. Now we're going to do 2/3. Well, 2/3 of 1 is almost like 0.6. The easy one here will be at 3. 2/3 of that is the 2. And we have the same thing going in the other direction. So we're going to have y equals 2/3 absolute value of x. Now we're going to take every one of those and go to the right and one up. So our final graph is going to be y equals, or g of x, however you like to write it, 2/3 absolute value x minus 2 plus 1. Our domain is always all real numbers that has interval notation of negative infinity to positive infinity. The range goes from the smallest number, which is 1. So your y values is greater than or equal to 1. So that would be our smallest value to our biggest value for interval notation. The end behavior is when x approaches negative infinity, the function approaches, when we look to the left, the function is going up. When x approaches positive infinity, when we look to the right, the function goes up. Goes towards positive infinity. They're going to go in the same direction every time with an absolute value. In our comparing, the parent function, there's no reflection, so it's shrunk vertically by a scale factor of 2/3. Translated 2 units right, because remember that's always going to be opposite of what you think. Because it's x minus 2, it's going to move to the right. But it is going to move exactly the correct way for your k value, vertical. So 2 units right and 1 unit up. Number 1, we can look back at that. Looks like I missed the end behavior. So when we look to the left, the function goes down. When x approaches positive infinity, when x goes to the right, the function's going down. So we have a parent function. Reflected over the x-axis. And it is translated 1 unit left, 3 units down. That was the question 1, comparing. Okay, another way that we've talked about graphing absolute values, we can use the vertex, which says that we can go 5 to the left and 2 down. And we would use our slope to the right of -3. So our domain is all real numbers. Our range are the y values less than or equal to -2. interval notation for that. The smaller number would be negative infinity, the larger number would be negative 2. It equals negative 2, so you have the square bracket. Negative infinity to positive infinity, because it goes forever to the left and ever to the right. The end behavior, when we look to the left, we find out that the function goes down. And when we look to the right, we notice that the function also goes down. We know that the end behavior is going to be the same for every absolute value. The same meaning they go in the same direction. They could both be pointing up or they could both be pointing down. But they will go in the same direction. The comparison to the parent function. The parent function was reflected over the x-axis vertically stretched by a scale factor of 3 and translated 5 units left. Remember, that's going to be opposite of what you think for the h value. 2 units down. And that's what a negative 2 would imply. So looking back over at our final graph, don't forget to label your equation. Now we look at writing equations. We see that our slope okay, it's not up 1, 1, 2. Looking here again at our slope, and the slope's a little tricky. It's not up 1 over 2. It's not up 1 over 3. It's not up 2 over 5. It almost looks like it's up 2 over, up 2.5 over 6. 2.5 over 6 is what it looks like. Rise over run. Not a very good example. Definitely not a test or quiz question. But if we times this by 10 and we times this by 10, we're going to get 25 over 60. We got rid of the decimal. Then we can reduce that by dividing by 5. And we'll get 5/12. That's what I'm going to call the slope. And it's translated none right or left. And it's translated 4 down. The domain is always all real numbers. And the range is from 4 down. That's the smallest number. And up. So our end behavior, when you look to the left, the function's going upwards. And you look to the right, the function is going upwards. These results will always match each other. So here we have a slope down 3 over 2, test it again, down 3 over 2. Pretty much. So y equals negative down 3 over 2. It's translated to the left 2 and up 4. The domain is all real numbers, and our range are the y values less than or equal to 4. Interval notation. Our end behaviors. We look to the left. The graph is going down. This would be an arrow and an equal sign. We look to the right, positive infinity. The function is also going down. These will always match in the absolute value. Look to the left, the graph goes down. Look to the right, the graph goes down. On the flip side, we're going to be solving our absolute value functions. You want to first be sure that your absolute value function is isolated and all by itself. So we have that, and it equals a positive, which is a requirement. So 1 minus 2x equals 9, and 1 minus 2x equals negative 9. What's inside the absolute value could have been a positive. What's inside the absolute value could have been a negative. So two different ways, and the absolute value made it look positive. So we'll subtract and divide by the negative 2. We get negative 4. And x equals 5. There shouldn't be any extraneous solutions here. But if we plug in our negative 4, we get positive 8 and 1, which gives us the square root of 9, which is 9. Plug in a 5, which is 1 minus 10, which is negative 9. Absolute value of that is positive 9. So the work would check out. Here the absolute value is equaling an expression. It has a variable in it. Now this expression looks negative. You might think it's impossible to have an absolute value equal that. That just means that the x might need to be, or would need to be, negative number. So we're going to say x plus 24 equals negative 7x. Write it just the way it is. And then x plus 24 equals the opposite of that expression. So I will subtract the x. Typically I like the x to be positive, but just to have the least amount of moves, we get x is 3, and in this case this gets to be positive 7x, so that turns into a 6x, and when we divide there, we get x equals 4. So we have two answers, x equals negative 3 and x equals 4. Well, when you check x equals negative 3, you get negative 3 plus 24, those are in absolute values, negative 7 times a negative 3. This gives us 21. Absolute value of 21 is 21. And two negatives make a 21. So check. That worked out perfect. On this side, we're going to take the 4. So we get 4 plus 24 in the absolute value bar. And we get negative 7 times 4. So we're going to get 28, and the absolute value of 28 is 28. But in this case, we get negative 28. They do not match. That makes 4 an extraneous solution. So we need to write extraneous solution next to the answer and put a light X on it. Only circle the answer that counted. You can always watch that video again and revisit what we talked about. What this meant is we set our absolute value into two different equations like we always have to. One exactly the way it's written and one with the opposite. Because what's inside the absolute value might have been positive and it may have been negative. We solved them. We got two answers. But because of the sign switching, this actually made it look like it was an answer, but mathematically it was not an answer. That made it extraneous. By checking it, we could tell. So first we have to isolate. Don't forget to isolate your absolute value. Then we're going to write it as a positive, and we're going to write it as a negative. We'll subtract our 6 across. Becomes 8, and we can divide. Get negative 8/3. We'll subtract our 6 across, and we'll divide. We get our two answers. Remember, one way to check that. One way to check that is to use our graphing calculator. So we're going to come over to our graphing calculator and we can type in our equation, which was the absolute value and looking at our equation again, that was 6 minus 3. It says K, but we can't use a K in our graphing calculator, so we just say X. Plus 8. That's what we have. Our other equation is 22. It doesn't matter where you write them. Just be sure that when you graph it, you get your 22, and then you get your absolute value. Now this is kind of funny looking. I had my windows from a different problem. So hitting zoom number 6 puts it back to this normal way to graph. And you might not be able to see anything but just that little vertex, because you know your window needed to look up higher to a maximum of over 25 or over 22, which is like 25. Then we could see more of the absolute value. Second calc down to intersect. Now up top it asks, is that one of the equations that we're working with? Yes, that's the blue line. That's the equation of the red line. That's the absolute value. So you agree to both of those. You hit enter for both of those. Now notice there's two answers. So I'm going to get closer to the answer I'm interested in and hit enter. It tells me it's at negative 2.66. Well, three is going to go into here. negative 2 times, which is negative 6, with 2/3 left over, negative 2.66. We can also say second trace. Go to number 5. Is that the equation that I'm looking for? Yes, that's one of them. This is the other one. And the solution this time that I'm looking for is closer to this side. I hit my answer. I get 6.66 and an answer of 22. Well, 3 goes into 20 6 times, which is 18, 19, 20. 6 and 2/3. So we verified, we checked it with our graphing calculator. If a calculator is available on your test, you can check your work. Not just get the answer, but you can check your work using your graphing calculator. So here we have an absolute value. So we're going to write this equation. Well, before I get started here, take a look. This absolute value is isolated already. And being isolated helps out a lot. But notice that this absolute value is equaling a negative number. Absolute values can never equal a negative number. Not when the absolute value is isolated. So this has no real solutions. That can't happen. You could graph this, you could graph that. You could type in the absolute value of 2x minus 14. We could type in the negative 12. We could graph that out. Remember, we have to look all the way down to negative 12, so we got to go to our window and look at our y minimum and make it more than negative 12. Or less, if you want to think about it like that. They don't cross. They don't cross anywhere. No real solutions for those two graphs. That's what this is asking. This next one, we take the 2x minus 3 and equal it to 3x plus 7. We take the 2x minus 3 and equal it to the opposite of, you got to use parentheses, 3x plus 7. So we will subtract the 2x. We'll subtract the 7. So we get x equals negative 10. On this side, we distribute the negative through. We add the 3 across. That gives us 5x. We add this 3 across. We added the 3x and now the 3. And when we divide, we get negative 4/5, or negative 0.8. Now we're going to check our answers. Because we have an expression here, so we might have an extraneous solution. If it was a constant number, besides just the negative like we had in 10, it pretty much implies that the answers given will be correct. You can always check it, but here we're going to check it. So we're going to check with 2 times negative 10 minus 3, that's in absolute values, and 3 times negative 10, that's not in absolute values. Negative 20 minus 3 is negative 23, that's in absolute values, negative 30 plus 7 makes negative 23, so that's looking pretty good. But notice here that when you take the absolute value of 23, that gives you a positive 23, and that does not equal negative 23. So this answer of negative 10 is an extraneous solution. So we put an X through there, we write the word extraneous solution. Over here, if it's a little complicated, and I'm a little short on space, I could say, do my math, go over to number, absolute value, and my equation again. There it is 2 times my negative, my negative 4 divided by 5, that's what I'm substituting in, minus 3. That answer is 4.6. And I could compare that to 3 times negative 4 divided by 5 plus 7. I got the same answer twice. The fraction that would have been shown would have been 23/5 would have been the fraction that was shown. I'll do that here quickly for us. I'll plug in negative 4/5 minus 3. That gives us negative 8/5 minus 2, but I need a denominator of 5, so that's got to be 10/5. So that's going to come out to be negative 18/5, which is a positive 18/5. Well, of course it's 18/5, but the number should have been a 3. So with a 3, it would have been 15/5, which is negative 23/5. And the absolute value would make that be a positive 23/5. And that's what we found when we did our calculations in the calculator. On this side, we would get 3 times negative 4/5 plus 7. That's negative 12/5 plus 35/5. Remember, that's got to be a value of 7 with common denominators. Positive 35 and a negative 12 is going to be 23/5. Check. It's a little complicated looking, but I showed you that you could do it with your pencil or you could do it with the calculator. 2 different ways. If the calculator is available, you can check with your calculator. We're going to write an equation that has a vertical shrink and it's translated so it has this range.
What's it doing?
So we know it's going to have a vertical shrink and the range, the small to large. So a vertical shrink means that the A value has to be less than 1. Pick any number less than 1. And the range has to go from 4 is the lowest number and up. So if we looked at the graph of this, we're going to be up 4, wider than normal. That would have a range of 4, y is greater than 4 would be our range. That's the interval notation for that. So we're going to write an equation of an absolute value function with a vertex on the y-axis. Has a reflection, so we know it's going to be negative. And it has to have a vertical stretch. So there's no need, or there can't be actually, an h value. We have to have a vertex on the y-axis. So it could be any number for k. So that graph is going to look like that. Vertex is on the y-axis, so h is 0. I actually didn't even need to use -5. I could use 0. Just -3 absolute value of x. That's another way. There's an infinite number of correct answers for the previous two problems. A couple more to go. We're going to state the domain and the range. The domain, the x values. What x values are being covered? 1, 2, 3. So -3 less than or equal to x less than or equal to 4. You could call that -3 to 4, and it includes both of those numbers. The range goes from -1 up to 4. Watch this guy. Up to 4 is your highest point. -1, including all the way up to 4. So -1 all the way up to 4, and it would include both of those. This one, this is to the 4th power, x to the 4th power, and it has it's a whole polynomial, but we have arrows that are pointing upwards. So our domain, in this case, it's going to continue to the left forever, it's going to continue to the right forever, so it's all real numbers. And the range is down here, 2, 4, 6. So y is greater than or equal to -6. You could say -6 comma infinity. You use the lowest number to determine your range. So here it looks like we're up 3, over 1, up 1, over 4, up 2, over 3, up 9. That looks like the square root graph. Okay, stuff we'll learn about in the future. So our domain are all the x values that are greater than or equal to 0. We don't have any values in the negatives. And our range are all the y values greater than or equal to 3. So you could say 3 comma infinity, and you could say 0 comma infinity for the interval notations. Sketch your graph of an absolute value function and a linear function with no solution. We've talked about this. I think we talked about it even with this worksheet. Think about what needs to be done. You can make any absolute value And you can make any linear equation that does not touch that absolute value. So here I made a sketch of an absolute value function and a linear function that have no solution. Good luck.